All right, good morning, everybody. It's a little less dark now than it used to be. Hopefully that's helping. How are you sitting with this black hole discussion? Let's maybe open that up for some discussion. Let's see, who did I not pick on? I said I'd pick on you last time, so what do you remember? I mean, yeah, according to the definition of the thing, the gravity is so intense in this region that nothing could ever escape. So the question is, could we ever send a space probe to one of these places? That will be really interesting. We could send a space probe there, and so that will, if it does end up getting crushed out of existence, that would be one story. And if it doesn't, then that will be a different story. There's a lot to be understood there, and one thing I wanted to bring up, and I'll show you later, but actually one of the guys who really developed the idea of the black hole, his name's Kerr, and he's gotten some notoriety lately. My wife actually brought this to my attention because he's kind of turned his back on the idea lately, and he's no longer believes that this idea of the singularity is a physically realistic solution to the black hole situation. So the whole concept of the black holes is in some sense much like this word dark and black in general in physics seems to indicate something we don't fully understand more than something we do understand. So yes, let's get some space probes out there. They're very far away though. The closest one of course is at the center of our galaxy, which is extraordinarily far away. So we'll see. That's going to be a while. All right, cool. Thanks, Tabitha. Let's see here. Right, yeah, so Peter, he brings up the point that there's actually very little spectroscopic difference between a neutron star and a black hole. And of course, there's very little difference between a neutron star and a white dwarf other than, a lot of attracting ability, right? A lot of gravity, as we would say, but not much brightness, right? And so the whole story from white dwarfs on essentially involves these non-luminous bodies that must be there due to the rotational dynamics, but we don't see anything bright there. And so the stories all follow from that. Yeah, that's a really interesting point. This picture of these black holes is very, very sketchy at the moment, so it's difficult to make any real definite statements about these things. And as we'll see, actually, we're going to talk about our galaxy today, and the organization of it. And the more that we try to explain things based on gravity, the more we realize there's stuff we can't see, right? And so by the end of this class, we're going to crack open this concept of dark matter, which is very similar to black holes. It's gravity playing out, but nothing seems to be causing the gravity. And the further we get into this story, because we're actually starting to work towards a bigger picture of not just what's around us, but the whole physical universe that we can see, the more sketchy it becomes that gravity doesn't seem to make sense at scales, right? By the end of this class, you'll see that something like 90 to 95% of the cause of all of the organizational gravity is invisible. So what does that mean? And I hope that we can work towards some answers for that, because this placeholder called dark matter, these placeholders to some extent called black holes, are very unsatisfying, at least to me, but I think to a lot of people, even the people that are working on these. And so the alternative solutions are very intriguing, and there's a number of them. I mean, a huge part of this discussion concerns the two big principles that I've tried to impress upon you that I think are the biggest revolutions happening in astrophysics. One is, how old is this place? And two is, what are the stars' material structure, right? Because the story that we've told about these stars living on the main sequence, basically in place, with respect to their temperature, and then having this death that results in them becoming very dim and bright, actually very hot, dim and hot. And then sort of either exploding or fading away. It doesn't really include any story for stars just sort of petering out, mainly because it's not interesting because it would take too long. Well, if it takes a really long time, if the universe has been around for a really, really long time, much longer than say, the Big Bang cosmology would allow it to be, then we have a great deal of time for a lot of cold stuff to be piling up. And if there's a ton of cold stuff piling up, we wouldn't see any light from it. And that might be the most sane explanation for all of this attractive stuff that we can't see. So I think that's going to be a really interesting thing to sort out in the future. And we'll get more into that as we go ahead. All right, let's get a couple more people queued up here. Yeah, you brought up these supermassive black holes at the center of galaxies. We're going to play more with those today. It's really interesting because the center of galaxies is the brightest place in a galaxy. And so, I sort of walked you through, there was this very popular picture, quote unquote, picture of a black hole that was released to the popular media and so forth about a year ago, which is really interesting because it's actually a serious Photoshop job on that thing. I mean, they've screened away almost all of the data to get this picture, because the fact of the matter is when you look at the center of galaxies, you see a bunch of bright stuff. You don't see a big region where no light is escaping from it. So the direct observation is essentially impossible. The real trick is trying to make sense of the rotational dynamics of things around them. And I think this is further complicated, and I'll talk more about this later, but it's all further complicated by the fact that, well, general relativity treats bodies as point masses, right? So the Earth is a point that has some attractive ability, right? Now that's a completely valid assumption outside of the Earth, right? If you're out here at the edge of the Earth, you may as well treat it like a point mass because all that material is under your feet, right? But what happens as you move in towards the center of the Earth? Now, from a more rational perspective, in my opinion, you're actually getting pulled by all the atoms in every direction. So the same problem we run into with the galaxy itself, right? At the center of it, is it reasonable to treat the whole galaxy as a point mass at the center? And then say, well, things are like rotating around this point center, so the thing at the center needs to be enormous. It's like, maybe that's not entirely reasonable. And I'll unpack that idea a bit more as we get further down this. But needless to say, I think this confusion about gravity is really critical in all of physics right now. There's this, I'd say the biggest problem in physics, or like the biggest, not problem in like the sense that it's a crisis, but in the sense of that everyone is working on, is trying to unify the very small quantum mechanics with the very large, so general relativity. And people are looking for this thing they call a quantum theory of gravity. And what they're looking for is how in the world the little parts of the atom are stuck together gravitationally, right? Now, to me, that seems like a little bit of a confusion about what gravity is, because gravity was actually established with respect to how atoms themselves are pulling on each other. So I'm not sure why in the world you would expect atoms inside of themselves to be doing anything gravitational at the same time. And so I don't know, it seems like a little bit of a fool's errand in trying to describe gravitation below the level of the atom. And it's very similar to the idea of treating, of making these assumptions. Every single thing that we do in science, we have to make assumptions about our system before we can process it. And the same thing seems to be playing out here with a lot of these gravitational dynamics. It's like, well, we'll just treat this like a point mass as opposed to like a physical body that's doing something. It seems to be, there's a lot of problems resulting from that. Of course, mathematicians who sort of rule the roost in a lot of these theoretical physics domains, they're more concerned, the concept of mass is perfectly fine for them to calculate gravity. And it works really well as far as our spaceships and stuff are concerned, right? But from a physical perspective, it might not be the most appropriate way to discuss what's happening. So it's an interesting little blind spot that's going on right now. All right, let me get one or two more thoughts. Yeah, well, that's come up over and over again, and that feeds. So she just has brought up the black body spectrum, the inability to take a plasma, let's say, ionized gas and produce a continuous rainbow on Earth. I mean, I think it's worth mentioning because it can't be stated enough. And the reason that it matters, of course, is because the reality is if the sun isn't a ball of gas, then it can't be crushed down into anything like a white dwarf or a black hole or anything like that. If the sun actually has a lattice structure, if it has a real material basis, if the hydrogen is in some sort of exotic liquid form, which is now known to be a very valid form of really high temperature, high pressure hydrogen, then it's essentially incompressible. Liquids, of course, in chemistry are incompressible by definition. That's the reason that, hydraulic systems even work in the first place. If you could compress liquids, you wouldn't be able to do work with them in hydraulic systems like, those cherry pickers or airplane wings or wherever you see these hydraulic systems. So that's a huge problem because it means that the story of the death of these stars, if this becomes an accepted idea in science that the stars actually have a material structure, in other words, they're something, at least their surfaces that give this black body spectrum are indeed something liquid-like, then the whole story that we've been talking about with these collapsing stars and white dwarfs and neutron stars and black holes is completely off the table, and something else has to appear. And it might be something a lot more mundane, like stars drifting down the main sequence, cooling off, turning into dark, invisible, almost moon-like, planet-like things that could be quite large, quite metallic or carbonaceous, silicate, not too far off from the thing that we're standing on right now, which was, of course, an idea proposed back in the 60s by the Soviet scientists who were somewhat at odds with the West in general and couldn't care less for our ideas about cosmology. So they were a bit untethered from that. And in particular, this one scientist named Oparin made this suggestion very long time ago. And it, of course, didn't make its way into the Western canon, but it may be coming back. So I'm glad you brought that up. It just can't be overstated. That and the timeline of things are the two biggest constraints, right? The material basis of the stars, whether they're gas or liquid, versus the timeline, whether the universe really started 14 billion years ago or whether it's been around a whole lot longer than that. Those 2 points are really on the ropes right now. And if and when and how those timelines and those understandings of stars change, they're going to completely rewrite everything that's in your textbook right now after the point of the main sequence story, which I think seems to be pretty valid. So, all right, thank you. Anybody have any questions or final thoughts about black holes? We'll keep coming back to them. They're very emblematic of a bigger process going here. Any thoughts? All right. By the way, guys, feel free to interrupt me throughout this. I'll try to note your participation after class as much as this. All right, so we're going to start talking about our galaxy today. Before we get there, I just want to mention a couple of housekeeping things. This week, I believe you don't have a Flipgrid assignment, so I did post the final project, which is basically a bigger Flipgrid project, where you're going to pull in a couple of different articles and reference them with respect to some topic that you're interested in. If you don't like any of those topics or articles, you want to explore some of these other ideas that we've been talking about in class, you're welcome to. Just come and talk to me first so that I can make sure you're on the right track with that. As we're actually rebuilding this course, I'm rebuilding this course for next year so that we can get it into the GE capacities program so we get more first-year students in here. It's kind of a tragedy that happened this year because in the Department of Physics and Engineering, our department chair left over the summer kind of abruptly. and didn't submit this course as they reformatted the general education requirements. So basically, nobody was getting GE credit for this unless they were grandfathered in. And so we have very few students this year compared to last year, which is kind of a bummer. So anyways, we're reformatting this class, and the biggest change that we're going to do next year is that these projects and a lot of the flip grids and assignments are going to be more geared towards you guys coming up with your own hypotheses of what you think could be happening. And you don't have to be right about it. It's more just like, okay, here's an anomalous thing, right, that doesn't make sense. What are the other possible explanations for it? And I think that'll be really healthy because there's this very bizarre aspect of the scientific training pipeline right now where you guys, any of you that have been through high school science or college science, you do a lot of technical stuff where you learn how to run these experiments that people have done before you, but you don't do a lot in the way of the creative, generative idea of explaining what the heck is going on. And that seems to be a huge problem in the world right now in science where people are really good at dotting the I's on these theses that have been around for 50, 100 years, adding little details to them, but there's not a lot of innovation in the basic sciences. There's not a lot of people coming up with really groundbreaking new ideas about things. And it's not because things don't need to be explained, it's just because the training seems to be more geared towards technical stuff as opposed to the creative aspects. So we're going to try to bring that in. I say all of this because if you want to do something more in the hypothesis generation side of things for your final project, that would be excellent, but that's not the way it's written right now. So come and talk to me if that's interesting to you. Questions about the final project? I also have this creativity project. I totally recommend you do that, especially if your quiz grades aren't where you want them to be, or if you've missed some classes and haven't had a chance to send me some recaps.
When are both of those due?
I'd have to check. 18th? Yeah, I think it's right before finals, basically. Yeah, I didn't want you guys to have to be doing that during finals as well, so get it done beforehand. Actually, just do it as soon as possible, honestly. Yes?
I have a question about the art assignment. Do you prefer traditional or digital medias?
Either's fine.
Cool.
Just take a picture, yeah. You can upload it to Moodle or to Flipgrid. So,
I liked your reference to Plato's allegory of the cave, kind of pacing what we really understand in science today. And we only know what we know and what we see. That's the limit of our understanding.
yeah, I think that it's so funny that he mentions Plato's allegory of the cave with respect to a lot of this stuff. And it's so funny that, a 2,000-year-old parable, more than that, is still at play in the world. Despite all of our technological progress, I think we very much are living out an allegory of the cave with respect to a lot of this. Now, again, the distances we're talking about are just unimaginable, right? And so the story that I'm going to get into here today is the story of discovering that we're even in a galaxy and that there's other galaxies, which might shock you to realize that that happened really recently. So most people, for most of history of astronomical observation, thought that the whole universe was here, and all the stars that were around us were the whole universe. And the fact that that turned out not to be the case was completely shocking to people. So when we see these ideas, I don't think that we have to be ashamed of the fact that we don't understand them. I don't think it's embarrassing that 95% of the matter of the universe is invisible, and it doesn't make sense. It's like, that's just where we are. We've been at this project of modern science, quite honestly, it seems like for maybe 100 or 2 years, right? I mean, you could say the modern science began with Galileo, but that's a stretch. It's like, we've had good instruments and so forth to examine the sky for like maybe 100 years. Maybe not even, maybe 50 years with these really good radio telescopes and stuff. So, yeah, we're still in the cave, we're still looking at shadows, and we're still trying to make sense of it. To that end, so this is the article. I posted a link to it on your Moodle from last week if you want to read the whole article. But I think it says a lot when somebody who can come at the end of their career, who's basically, lived a life of fame for having discovered general relativity solutions that provide for black holes, to say, you know what, I think that this mathematical anomaly is not a physically useful model for what's happening here. I think it doesn't make sense. I think that's a really bold claim for this guy, for Roy Kerr to come out and say, and I think we'll see more of that, right? It's interesting how people at the end of their lives feel a little bit untethered often from the pressures of their careers and so forth. Some of my favorite people to talk to on the podcast are these like 90-year-old scientists who are completely retired and don't care at all for whether, they've already had their career, they've had their fame, they've had their success, they've had their families and everything. And it kind of frees them up from the pressures of needing to conform to their old ideas. And so these people at the end of their lives are actually really fascinating because they tend to be more honest with themselves about what's happened. So it's going to be tricky, though. I mean, Roger Penrose got a Nobel Prize for black holes. There's been a lot of illustrious careers built on the back of these really extraordinary conclusions, regarding these almost science fiction ideas that we see. It's actually kind of funny. So, you might have heard of this idea of like a wormhole. So at the center of a black hole, like physics breaks down and maybe it can link to other black holes and all of this. This was actually an idea that Carl Sagan had for a science fiction book he was writing, which was later turned into a popular movie. I believe it was called Contact. Could be wrong about that. Is it? Yeah. The funny thing is, so Carl Sagan had this idea for a wormhole just for his science fiction book, and he went to one of his friends who was working on these black hole things, and he was like, can you make this like a reasonable idea for me? Like, can you show me what sort of circumstances would allow this to happen? And so he essentially invented the idea for a science fiction novel, and it actually, the work that was gone into trying to defend the idea for the science fiction novel and make it believable ended up becoming part of the actual scientific discussion after that point. And I think that's very significant in some sense. A lot of good ideas do come from science fiction, but it is still science fiction at the end of the day. So let's keep going with this. Today, we'll talk about the Milky Way, and we're going to work towards understanding our galaxy in relation to other galaxies. Of course, the best one for our understanding is this guy that we are sitting in the middle of. Now, we have some huge questions like how does this thing form? How is it sustained as well, which is really interesting because it's a large-scale organization of stars, and it seems to be perpetuating in some sense. So what's the process that leads that to be a stable structure? We're talking about something in our own galaxy of like 500 billion stars. God knows how many planets and everything else. So there's a lot of things happening here, and they all seem to be organized. And that's a really complex and nuanced story to try to tell. Now, people have been talking about the Milky Way forever because you can see it, especially in the summer, when actually we have a good view of the center of it, where it's really bright. I'm sure you guys have seen it out if you go out away from the city a bit, where the lights are. You can see this incredible thing, and people have been seeing that forever. And you can only imagine, 2,000 years ago, before electric lights, how dominant of a feature that would have been in the sky. And so it serves as the basis for a lot of mythology for ancient people. There's every single people's have a different story for this, but they're all somewhat similar, which is interesting. The Babylonians are perhaps the most well-known story, and the Babylonians have the Milky Way being the severed tail of that dragon Tiamat, who's slain by their central deity Marduk, right? And I think that's actually really interesting that they would place humans at the center of this cosmic battle against the dragon, and in some sense, I think that's just reflective of how central that story is. And I won't go into it all over again because we spent a day doing that. But obviously, there's beasts to be slain in everyday life, and I think that was a really central piece of the story. And of course, Marduk was the god king, right? The kings of the Babylonian society, the Sumerian societies, reflected and inhabited that actual role as the Marduk who slays this demon. So they perpetuate this in the story, and that's how they saw the Milky Way as the remains of this slain dragon that's sort of encircling them. And in some sense, that makes sense, right, as the proper place for a person in a well-ordered life. The Greeks, of course, pick up this tradition. They have a not-so-different story. I won't get into the details of that for lack of time. What's kind of interesting, actually, is over in the Americas, the Quechua Indians, they also have a kind of similar story. They see all sorts of different animals and like sort of semi-deities arrayed in the Milky Way, but they actually shape their creatures by the shadows, which seems to be wholly unique. So most people are seeing the stars carving out different gods and so forth. But the South American, Central American Indians seem to have seen it as the shadows being the actual, I was going to say organisms, but let's say deities. All right, so let's flash back to our Western story a bit, because it's where we have our most information, starting with the Greeks. Of course, the Greeks were the first people that actually, and not all of them, but a few of the rebels started thinking about things in terms of the actual material organization of these things. Like they must be some sort of substance doing something. So one of the first records we have of this, by the way, when I talk about these really ancient Greeks doing this very rational science for the first time, we actually don't have their writings, right? So one of the first people to write about the galaxy was, of course, Democritus. Now, Democritus gave us the idea of the atom for the first time, too. But we don't actually have Democritus's writing. We have, at best, rehashings of it, which are handed down to the Romans, who kept the actual archives and the stories. And so you're hearing like a game of telephone. So we don't know exactly how they thought about these things.
Because the Library of Alexandria? Was that wrong?
That was much later. But yeah, certainly that was a nightmare that we lost that. And I often think about how all of our knowledge today is on the internet. It's open to a very similar crisis as the Library of Alexandria. Hopefully I'm wrong about that. Hopefully it's robust enough and decentralized enough, which is actually in some sense a good sign, right? The internet doesn't live on anybody's single computer. And so there's a lot of computers everywhere that hopefully keep us, in some sense, bolstered against those kind of disasters. But, we don't have these original writings from the Greeks, and that's really interesting. What happened to them? Well, paper doesn't last that long, right? And the reason that we even have some stuff is a lot of the best paper writings come from Egypt, actually. And the reason probably being that it's just so dry there that these things could actually be preserved in a way. The same is true with Canaan, right? And a lot of the old Hebrew texts, the original, like the Dead Sea Scrolls, things like this, they were housed in these very dry locations. And so the records could be kept. But the rest of it is essentially a game of telephone. So, and of course, the Romans who were writing down the stories of the ancient Greeks, yeah, in some sense, they were cultural inheritors of the Greek traditions, right? They adopted a lot of their architecture and they modified their myths and so forth. But the modifications weren't insignificant. And so a lot of the stories and retellings were reflective of their own desires as a people and the way that they had constructed their society, which was perhaps very different than the Greeks. Also, sorry?
You can see that a lot in their theater. It's a lot more violent.
Interesting. I didn't realize that. Yeah, that's interesting. The Greeks also, it's difficult we often talk about them like they're one homogeneous people, but it was kind of more like the United States or something, right? Like if you go to Louisiana, it's going to be very different than Oregon, right? New York's going to be very different than California. These are almost like different peoples, right? And I think that's a huge trouble with our country right now, is trying to keep some sort of unified sense of a nation together. It's very tricky because everybody has completely different cultures in all of these places. And the Greeks are very much like that. They're island peoples, right? So every island had its own academy, its own way of thinking about things, its own preferences and cultural norms. And so in some sense, maybe that's why we don't have this monolithic preservation of their ideals and of their writings and so forth, because they weren't really one big powerful people. They were just a bunch of smaller powerful peoples. All right, so there's some glimmer of talking about the Milky Way as the glow of stars that aren't quite visible. These guys seem to think that, now of course, hold that thought. So of course, when you look at the sky, and like I mentioned with the Quechua peoples, there's a lot of dark regions in the Milky Way too, which is really interesting. Those turn out to be dust, we realize today. And we talked about this when we were talking about the interstellar medium before. But people are trying to make sense of that. So these early Greeks seem to think that, in some sense, the Earth's shadow was actually blocking off the light to these stars. Of course, they thought that the sun was illuminating a lot of these stars as well, right? So they were being lit up by the sun in some sense. Now, this didn't play out very well. We'll get to that in a minute. Aristotle comes along a bit later, also a Greek scholar, a bit later. He suspected that the Milky Way was actually part of the Earth's atmosphere, and that the appearance of its cloudiness was actually due to refraction in our upper atmosphere. Not even too long after that, the critics lined up and said that if that was the case, then you should have some sort of parallax effect. So when you traveled, you should see different parts of the Milky Way, and that didn't really seem to play out. So this idea didn't hold for very long. If we cruise through the Dark Ages, right, so very little happens for like 1,000 years. The Persians start to actually develop some really intricate astronomy and mathematics. One particular astronomer, Al-Biruni, suggested for the first time essentially that the Milky Way is a collection, quote, of countless fragments of nebulous stars. So they're little pieces of stars, which is kind of getting us pointed into the direction that we're headed today. This Spanish astronomer, Avampache, proposed the Milky Way to be made up of actual stars, but appears to be sort of squished together by the Earth's atmosphere once again. And this line of thinking continues all the way up until Galileo. So Galileo is kind of the first person who was able to pick out individual stars in the Milky Way for the first time. And actually people who followed him and used that same technology, the telescope, the very newborn telescope. Remember, that telescope didn't come online until about the 1600s. So we've skipped ahead from the Greeks by almost 2,000 years at that point before we're actually able to pick out that this big, blurry swath seems to be actually made out of stars for the first time. And it's really ironic. So about 100 years after that, this philosopher who we owe essentially our model for solar system formation to, Immanuel Kant, comes up with the idea that, hey, he comes up with the idea that that there is a solar system sort of rotating and that it forms by this collapse of gaseous precursor stuff. But he also has the same idea about the Milky Way, which is really prescient, because that's essentially the idea we have today, that all of these primordial swirling parts would come together, and that what we're actually looking at is the side view of this giant, what he would have called basically a spiral nebula, something that's swirling in on itself, made out of all of these stars, which turns out to be very close to the picture we have today. And it's kind of ironic that, have you guys read any Kant in your other classes? Nope. That's okay. It's a bit ironic that Kant had all of these long-lasting ideas about the natural world, because Kant championed, he's probably most famous for this idea of transcendental idealism. And the foundational basis of transcendental idealism, it's a mouthful, basic idea is that the world is essentially unknowable, that everything we see is just a matter of our own perceptions interacting with the world, and so we can never really get at what nature is, because we're always confounded by our own perceptions and so forth. I think that's really interesting because, in fact, he does supply all of these natural hypotheses. But he says at the same time, I wouldn't trust him, essentially. He's like, this is an idea, but it's probably wrong because we're humans and we just can't actually know what's going on out there. So space and time are just features of how we perceive these objects. They're not the things themselves, which is also really interesting too, because indeed I would agree that space and time are features of how we perceive things, but they've of course been turned into actors in the modern day with the advent of relativity and so forth. All right, so the Milky Way, Kant coined this term island universe, which is really, really, really ahead of its time, because people, and I'll start talking about the debate in a minute, but people were fighting, tooth and nail for whether the universe existed beyond our Milky Way until the 1930s. So for 200 years after Kant's introduction of this idea that, these other nebula that we see out in the sky, maybe those are actually other galaxies just like ours. First advanced in this, like 1755? But people didn't agree on that idea until almost the 1940s. So it's interesting how these ideas can crop up and they can live for a very long time. That's why, when we're talking about something like the black body spectrum of the sun, it could be 200 years before people agree that that's a serious thorn in the side of the gaseous star's story, right? It's, in some sense, these ideas are very painful because they force you to rethink your entire perspective on what this place is. It was very convenient, of course. Maybe that's not generous enough. It fit very nicely with a lot of the cosmological, theological stories of the time that the sun and us and Earth would be at the center of the universe, right? That's a very, it's a nice picture. It would be nice if it were so. And it helped people understand gravity in that day as well, because, well, of course, if we're at the center of everything, why shouldn't everything revolve around us, fall towards us, etc.? So moving beyond the idea that this is the only galaxy, that everything is here, was very, very painful for people, despite the fact that it made a lot of sense even in 1755. It took 200 years of people rejecting that idea before it was eventually, it became painfully obvious, let's put it that way. Much as I have argued in this course that the material basis of the sun is sort of painfully obvious, but it could take 200 years for that to be a genuinely accepted idea, which is really interesting. I think that's something I really hope you guys can come away from with this course, is just how slowly our minds change as people sometimes. Even in the face of completely glaring evidence, it's just very, very difficult for us to change our minds. For better or for worse, I think it ballasts our civilization to be slow. We don't really want our science to be flipping all the time, right? We don't want it to be so fickle that we can't make any decisions whatsoever. So in some sense, it's good that this thing is ironclad and it's very difficult to move. But in some sense, it's bad because it holds us back. And there's probably a healthy balance to be struck there. All right, so the first person who tried to actually make a picture of this thing was William Herschel. We talked about Herschel back when we were exploring in the first couple lectures about the history of people debating the material basis of the sun. Now, Herschel and his son, or was he the son? There's two Herschels, John and William. I can't remember which came first. The one of them was actually proposing that there was people living on the sun underneath the sunspots, which is really interesting. And actually the fact that in a distant age, this was back in the late 1700s, early 1800s, that you could actually hold such wild ideas and not be, canceled as a result of them is really quite interesting. So these letters between people were just exploring all sorts of wild possibilities, and some of them turned out to be true, and some of them were just completely crazy. And nonetheless, these ideas were entertained. So he started making this map, which you can see here on the screen. He put the solar system still sort of close to the center of it, which maintained this idea that we are at the center of things. Of course, at this point, people are still leaning towards the idea that the galaxy is all there is. This is the whole universe. Now, around maybe 100 years later, this guy named Lord Rosse This is in 1845. He builds a really good telescope, and he starts to see that there's these things that they were calling nebula, these clouds that were beyond the Milky Way, actually appeared to have some spiral structure to them sometimes. And this sort of glued together with Kant's idea of this island universe and started up a huge debate. So the first piece of evidence that really started to turn the tide, but not in any timely way, was this guy, Heber Curtis, who started looking at nova in these little nebula. And he essentially noticed that, first of all, there was a lot of these nova occurring in these tiny little regions of the sky, much more than were occurring in the galaxy. It's in our, in the Milky Way, let's say. But out in these little spiral nebula, there was a lot of nova occurring. Furthermore, those nova seemed to be way, way more dim than the ones that we did see around here. So there had been a few nova observed, right? And they were really, really bright. In fact, the Galileo's nova was persisting into, you could see this star in the daylight. It was in some sense competing. I wouldn't say competing, but it was bright even next to the sun, right? So they're really, really, these explosions are huge. And we were seeing more of them and dimmer ones in these spiral galaxies. So that's got people thinking, wait a second, maybe these are whole organizations of stars and they're really, really far away. But the proposal of how far away they were became a thorn in the side of these theoreticians because people couldn't accept that something could be something like 100 light years away from us. That was just an unimaginable distance to people. So there's this guy who really took the other side of the debate named Harlow Shapley. And that was the backbone of his argument, was essentially, they were talking about Andromeda at the time, which was thought of as just a little nebula. And he said, look, if Andromeda is not in the Milky Way, then it's got to be 108 light years away. And most of the contemporary astronomers couldn't accept that kind of distance as being possible. Now, there was also this fact that there was an observation of a nova in Andromeda that seemed to actually be brighter than the entire nebula itself. This was inconceivable too, because people had never seen a nova that big in the Milky Way. Now, we do realize that these things, we call them supernovas now, they do actually occur in the Milky Way. They're just incredibly rare. So, I think the thing that actually won this debate at the end of the day for Curtis was noting that the actual velocities of the rotation of these spiral nebula were too fast to have been actually inside of the galaxy. In other words, if these nebula were part of our own galaxy, they would be in some sense anchored into the rest of the galaxy in a way that wouldn't let them to rotate autonomously. And so all of these little pieces of evidence seem to have really sunk the deal. It was followed up by the discovery of these Cepheid variables, which we spent some time on previously. And the Cepheid variables, of course, are part of this standard candle argument, right? Where the way that these stars pulse gives us some idea of how bright they really, truly are, right? So if we see a pulsating star that fits this Cepheid variable characteristics, and it's dim, but it has these pulsating degrees, then we know how bright it truly is, which means we know exactly how far away that headlamp is from us, right? And so all this work was actually done by this woman, Henrietta Leavitt, at Harvard, who was studying all of these things during, essentially, while World War I was kicking off and all the men were away killing each other. So she pretty much, I think, put the final nail in the coffin because they were seeing these Cepheids in these other spiral galaxies, and they appeared, they called them nebula, spiral nebula at the time, but they were clearly really, really, really far away is the thing. So that was essentially the end of the debate. And, we're all the way up to this point we're all the way up into the 1920s at this point by the time that people are really jumping on the bandwagon that, yeah, I think there's other galaxies out there for the first time. So that was only 100 years ago. It's really crazy. So I think that it's important at this point, in the story. We've been building a story across the course of this class. And that's what humans do. We build stories. It's how we make sense of things. But the back half of the story from this point out, the first half of the story, let's say, concerns debate across 2 millennia, 3 millennia, if we go all the way back, to the Babylonians and the Greeks. Like, people were trying to explain the sky for a long time. But nobody was thinking about the fact that there might be whole other worlds like this galaxy out there. And so the stories that we're going to be telling about looking beyond our galaxy are incredibly fresh. They're very, very inchoate and underdeveloped from this point. So I guess that makes sense, but we have to take everything that we're looking at after this point with a grain of salt, because we just haven't been looking at it for that long. So where do we go from here? Edwin Hubble built some of the most incredible telescopes in the 1920s that the world had ever seen, and he was actually able to finally, in the late 20s, pick out some individual stars in these distant spiral nebula and kind of, directly observe that, yep, those are not just balls of gas. For sure, they have individual stars, and they're extremely far away. So we have other galaxies for the first time. So now the task became trying to understand the structure of this galaxy. Okay, that little spiral thing we're seeing out there, I think that's what's happening here in our own Milky Way. So if we look at that, that should be telling us a bit about the structure of our own galaxy. And that's essentially the strategy that we've been taking to reconstruct our own position in this thing all along the way. So this is the map that we've built at this point of our own galaxy. And in some sense, it's aided by the production of radio telescopes, because remember, there's a lot of dark stuff in the Milky Way, right? Even in the brightest time in the summer in the northern hemisphere, when we can see straight into the heart of the Milky Way, there's a lot of black, cloudy stuff, right, getting in the way. It's very hard to see the center. Fortunately, radio telescopes can penetrate a lot of that dust. And so we can start to get an accurate actual picture of the composition of the interior and the density of the arms and so forth. And we can actually place ourselves into one of these arms. So that all comes back, and we can thank, in some sense, that 21 centimeter line for actually telling us what the dust is, what's going on, where this neutral hydrogen is, where the density of these arms is, because a lot of the arms is packed with neutral hydrogen, which doesn't give off light. It's packed with dust. A lot of the mass is not just in the stars themselves. And as we'll see, our own solar system is making this, hundreds of millions of year journey around the center of the galaxy. And as we do that, we actually pass through the different arms. So the arms persist. They're not just collections of stars. The stars are actually traveling through each of the arms. The arms are more persistent, stable structures than the stars themselves. So there's more to this than just the stars that we see. And a lot of this, we can thank the radio telescopes for being able to see this stuff. So let's see where we are. There's 2 main spiral arms here, and then a bunch of fainter arms and what they call spurs, these little dashed line portions of it as well. We believe now that the sun is near the inner edge of a short arm called the Orion spur, which is about 10,000 light years long. You can see it down there, maybe midway down from the bottom. I'll show you a close-up here. So there we are, the Orion spur. It's kind of a trailing off portion of one of these arms. Now, how's this thing organized in general? So in general, these spiral galaxies, and there's a couple of other types of galaxies. We're not going to do that today. We'll get into that more next time. And of course, the fact that there's different shapes of galaxies is going to be important in trying to tell the story of the lives and deaths of galaxies, which, if you think telling the story of the life and death of a sun is difficult because they last for millions of years, telling the story of a galaxy is exponentially more difficult. But we're going to stick with the spiral galaxy for now because that's the kind of galaxy that we're most acquainted with. So we see a few features that are pretty obvious with these spiral galaxies in general. One is this really thin disk where most of the cool stuff is happening, most of the stars, where we're located, in other words. And there's also this thicker disk around it, and then there's a halo, sort of glimmering diffuse region as well. Now, the basic theory goes like this. So the thin disk is young stars, gas, and dust. It's embedded in this more diffuse disk of older stars. So the older ones are sort of cast out from it, which I think is actually a really, and there's good reason to believe that, and we'll get into that in a minute. But I think that's really interesting because, as we'll see, as we work towards this story of dark matter at the end of the day, the problem is really that there appears to be too much stuff outside of the actual disk of the galaxy, something actually contributing to pulling on stuff from outside of it. And we're already at the point where we're understanding that the older stuff seems to drift out of the actual plane of the galaxy, which is quite interesting. And I'll show you how we know that in a second. So, close into the galactic center, the stars kind of bulge up in this central feature called the nuclear bulge. And the thin and thick disks are, of course, embedded, and the nuclear bulge are embedded in this bigger spherical halo of really old, faint stars that extend really far, like 150,000 light years from the galactic center, which is pretty crazy. So, we'll deal with this invisible mass in a moment, but needless to say, the standard model for the way that this whole thing moves cohesively requires that most of the mass is actually located something like 200,000 light years outside of the galaxy. And this is a central crisis in this whole story that we're working towards by the end of today. Now, along those lines, the galaxy doesn't seem to rotate like a solid wheel. Instead, the objects turn around the center more like a solar system, so the things that are closer in go faster, the things that are farther away go slower. We see that in our own system here, right? Mercury is cruising around the sun really fast. Pluto takes, I think hundreds of years to go around the sun. So this is interesting, and it lends credence to the idea for people that it is a gravitational system fundamentally. There's some details, the devil's in the details, as they say, and we'll get to those in a moment. Now, the problem initially with this was that if the stars were the only mechanism for holding these spiral arms together, then over time, the spiral arms should wind up and completely disappear. And most of the well, not most, but many of the galaxies we see have these spiral arms. They must have been around for a really long time, and there must be other processes to maintain them. And this is when people started really bringing in the idea that these arms were held together by non-star stuff. In other words, giant molecular clouds, just dust, just neutral hydrogen, the things we talked about earlier in the class, which actually have enough gravitational influence on their surroundings to maintain this cohesion over billions of years. So this is, I guess, a good point to bring in this picture. Because, okay, you've solved one problem because you can hold your arms together using all of this extra material that's not stars. The problem is that leads to this other problem, which is that on the left, we show how an actual gravitational system would behave with all of this material, right? This is very much how the solar system turns. But on the right is how the galaxy actually turns. And what's interesting, you can see, is that the outer arms keep up with the inner arms. In other words, the galaxy as a whole seems to have a lot more cohesive rotation than it does if it's simply a solar system type model. And this was extremely shocking to people. I'm not sure when this discovery was made exactly. I should have written that down. But needless to say, if you compare, let's say, the model of how things should actually be sort of slowing down in blue here as you get further away from the galaxy, the reality turns out to be far from that, in fact. And so this is where we actually run into this idea of dark matter for the first time. So what is dark matter? This is a great question. Well, the reason we call it matter is, of course, because there appears to be some gravitational influence outside which stabilizes the entire body. The reason we call it dark is because we can't see it. And it's a really interesting crisis in the whole puzzle right now. I had a friend while I was doing my degree who was he was in a lab, and his job was to try to build a detector to find this dark matter. And lots of people were working on this, actually. He actually ended up leaving that lab because it just seemed so hopeless and pointless to him. How do you actually detect something that's not there? It's a very tricky thing. This was a problem with neutrinos, actually, when I was growing up, too. They were hypothesized to be a real occurrence, but nobody could detect them since they seemed to really relay right through matter quite quickly. And so how were they going to do that? And they devised this really elaborate system, which ended up working out. And so there are neutrino detectors today. The hope is that they'll be able to do the same thing and actually detect this stuff that nobody can see. Now, the question becomes, is there stuff there? Are there actual gravitational invisible particles? There might be. The question is, are they some exotic form of matter, or is it just something really old and cold that we can't see, right? And in the meantime, before we can answer that question, we have made some interesting maps of where this stuff would be, right? And essentially, there's different streams of this, and it actually looks a lot like there's sort of an orthogonal one and a perpendicular stream, a halo of where this dark matter stuff should be. Which actually, anybody who was here last semester might recall the different moon systems of Saturn, which looked very similar to this, right? So you have, Saturn has this really nice ring structure up close, a lot of big moons, but in the distance it has all of these bizarre moons some of them are rotating backwards, there's different streams of it, right? So there does appear to be something which is distributed in a gravitational manner that could account for this extra tug on the outer arms of the galaxy. So what the heck is that stuff made out of? Well, it can't be ordinary stars because we'd see them, they'd be glowing. Can't be elemental gas because we can see neutral hydrogen. We can see neutral atoms now using this 21 centimeter technique that I talked about with the spin flip process. If it was ionized hydrogen, it would be emitting its own light, so it can't be primordial ionized hydrogen. If the hydrogens had cooled and stuck together, it would be forming a sort of dark feature that would screen out UV light, so we'd be able to see that too. Can't be a large number of black holes or neutron stars, since those would have a pretty serious X-ray emission to them. So what are we left with? What possibilities can we possibly have at this point? Well, of course, there's two serious possibilities that are being entertained right now, and then the third, which I've alluded to. One is that it's some sort of completely exotic subatomic material that nobody has any idea what it is, and that seems to be the most popular hypothesis right now. And if we build the right kind of detector, maybe we can get a grip on this, and it turns out to be a really foundational piece of the universe that we just can't see. Fair enough. Another popular, well, less popular, but still well-funded idea is that gravity, Newtonian gravity, Einsteinian gravity, falls apart at some point. Like, it works really well here in our local galaxy, but for whatever reason, and they're very nebulous about the reason for why this falls apart, but you have to modify gravity at these large scales. And I've talked to a few people working on this, and in some sense I find it just a little bit dissatisfying. If it is the case, then we should have a good reason for why that happens. But it seems like they just plug in a new field variable to replace various Einstein variables, which seems just like an ad hoc adjustment to me a little bit without any kind of answer. And so the third possibility, and I think the one that I'm probably leaning towards the most at this moment, is this idea of Rambos, which is a pretty funny name. Does anybody know? Are you guys too young to know who Rambo is? These astrophysicists and their naming structures. It's unbelievable. Okay, Rambo is Sylvester Stallone, right? That's the guy? Unbelievable. Yeah, he's just this like killing machine who's just running around with machine guns, just murdering people in some war zone. Okay, so the name of the RAMBOs. RAMBO stands for Robust Association of Massive Baryonic Objects. So in layman's terms, that just means cold stuff, right? Cold matter. So basically, well, the core, like the dead remains of stars that didn't go nova, essentially. Most of the work that was done on RAMBOs was done in the late 90s, from what I can find. And these guys, they didn't get a lot of pushback, but there's nothing exotic about it. And of course, I think the biggest reason that the RAMBO project was abandoned was because of the cosmological preeminence, that this paradigm that we live under, which says that the universe is only 14 billion years old. If you're gonna take a star and cool it off to the point that you can't see it anymore, that's going to take billions and billions of years, probably tens of billions of years, to take something like even our sun, but let's say stuff that's even bigger than our sun, and just cool it off for a really long time. It's going to take a really, 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 really long time. And the reason we don't have that much time is because this Hubble relationship that we're going to be working towards, which actually asserts that the universe itself is expanding, and that as it's expanding, we can trace it back to a point. And if we do the math on that, we find that that point started 13 and a half, almost 14 billion years ago. Well, that's not enough time to do very much at all, actually. If you think about the fact that, life on this planet is 3 billion years old, right? And presumably, the galaxy was here before the life was here, before the planets were here. You just don't have a lot of time for these kind of things to happen. So the entire narrative, again, is constrained by this cosmological argument, which is, just to preview it, the cosmological argument is really rooted in one or two, well, really two discoveries of the 20th century. One is Hubble's observation that things that are really far away are quite red, actually. The second is the CMB, which we'll deal with. We'll give it its due diligence here in a little bit. But needless to say, we talked about this Doppler shift. As things are moving away from you, they get red. And so the natural conclusion was, well, these things are moving away from us. They're very red when they're far away. Now, of course, it opens up the question of whether there's other reasons things that are far away might be red. For instance, the fact that, energy is essentially proportional in some sense to the wavelength, to the frequency directly. But redder light has less energy than really hot blue light, right? And so are there other ways that light could lose energy when traveling across extraordinary billions of light years? And people have argued over the years that that is perhaps a valid interpretation of this redshift distance relationship. But nobody has made a lot of those arguments are deeply mathematical, and it's very hard to persuade hearts and minds with mathematical arguments. So they haven't been really adopted so much. And of course, they fit so nicely into the Big Bang narrative. Now, the other thing that really cinched the deal for the Big Bang narrative was the CMB, and we'll give it its due treatment soon. But what's really interesting is today, one of the biggest crises in cosmology is that if you calculate the age of the beginning of the universe using the CMB, you get a different age than if you calculate it using the redshift. And you might say, well, that's just sort of error on the measurements. But the problem is that you can take that measurement from a number of points in the CMB, and you can take that measurement from gazillions of different redshifted stars, and you get really tight error bars on either one of those measurements, and they're not the same date that you calculate. And they're separated by several standard deviations. And so the fact that these two phenomena might not be even pointing to the same origin is increasingly troubling, I think. So what else could be going on? So we could have RAMBOs, we could have modified Newtonian dynamics, we could have exotic material, this dark matter stuff. I had the pleasure of sitting down with this Princeton physicist last year who was studying the heliosphere, so the large-scale structure of our solar system. It turns out that much like a great deal of the galaxy is just this like gas and dust, right? These arms aren't just stars, right? There's a lot of other stuff. In fact, it's a dominant portion of the arms. There's a similar thing going on in our own solar system. all of this solar wind actually forms into these structures. There's actually a nice blanket down the center line, and it's kind of sheathed in this material where the actual outflow from the sun is crashing up against the interstellar material, and you have the solar system kind of contained in this nice bubble. And the result of that is not only that it has a sort of structure that as a whole, the solar system is kind of like a bubble with a big long tail trailing out behind it, but you also have the accumulation of a lot of debris out at the edges of it. They call this stuff the Oort cloud, right? And this is supposed to be just a bunch of garbage, icy garbage. It's very cold out there. What's really interesting, though, I was talking to Eric about this, is that the one Oort cloud, say our Oort cloud, is essentially halfway to the next star system, which means their Oort cloud is essentially bashing up against ours, assuming our stars are facing each other. If they're not facing each other, the tail can drift out even farther than that, way beyond the Oort cloud. So you actually have a situation where these star systems are in some sense tangled up with one another, which I think is really, really interesting. And I haven't, I was talking about this with him on the podcast, and he seemed to think it was actually a kind of intriguing idea that there might be some Velcroing going between the star systems, right? And so nobody's actually studying this quantitatively right now, to my knowledge, but what I'm trying to get at is there might be other cohesive mechanisms available to hold these galaxies together that have nothing to do with gravity at the same time, right? In other words, if our star system's tangled up with our neighbor, that might be more of a friction type of situation than it has to do with gravity itself, us being stuck to the next star. Gravity is extremely weak, too. That's the other problem with trying to explain everything with gravity. You know, you don't have to get that far away from the Earth before you stop feeling it. So these seem to be the possibilities that we're left with. All right, so last few minutes here, last 10 minutes, let's pick apart what's going on at the center of the galaxy. And then we'll kind of move towards the formation models that people have come up with, which are very, very underdeveloped right now. So we won't mess around with them too much. Now, as we talked about last time with these black holes, people now believe that all of these galaxies contain a supermassive black hole at their center, which is equivalent to something in our own galaxy like 4.6 million suns. And it all fits within the sphere, which is less than the diameter of Mercury's orbit. Of course, we can't see that thing at all, right? Which is makes the whole proposal very difficult on an empirical basis. All we can see is that things are whipping around very fast at the center. Just to give you some sense of how difficult it is to see, the light from the central region of the galaxy is actually dimmed by a factor of 10 to the 12th by all of the dust. So that's 10 with 12 zeros after it, times the amount of, that's how much the light is being cut, right? So not 1,000th, not 10,000th of the light, but gazillionths of the light is making it out through this dust. So we can't really get a grip on what's happening there at the center, except through some tricky infrared and radio telescope observations. So let's take a look at those. So this is a radio map of the center of the galaxy. Not extremely great resolution on this thing, of course, but this whole area, we label this central region Sagittarius A. And this, of course, gives way to the idea that there's a supermassive black hole going on at this center point. If we take a look at it in the X-ray telescope, we get a little bit more detail here. Now, the X-ray emitting points are, of course, thought to be things like neutron stars, white dwarfs, the stellar black holes. And this is, of course, left over from this collapse narrative that we built out in the first, last week, I suppose it was. So you see the lowest energy in red, the highest energy in blue for these X-rays. Now, there's thousands of stars within just a few light years of Sagittarius A, which is the center point where this hypothetical black hole entity is living at. So you can't get a real solid picture of the center itself. It's also, there's a huge crisis surrounding this narrative too, which is how in the world do these young, you see most of the stars are these reddish main sequence stars, but there's a few of these really hot OB type stars, these really massive young stars, right? We don't think that those massive stars can live very long. So the question is, how in the world can you form a massive star next to this supermassive black hole? It doesn't make any sense. It's kind of like trying to explain, in some sense, the formation of a super dense planet in the formation process of the solar system, which we spent a lot of time on last semester. But how in the world do you make something so big and dense when you have this super hungry black hole right next to you that should be eating everything, right? I think this should set off some alarms for people about this theory. So there's no good explanation for that at the moment, for how in the world you actually have these young, enormous stars forming next to a black hole. It doesn't make sense. So what in the world's going on there at the center? We do know that the stars there are moving really rapidly around the center point, okay? So the question is, what's going on? I think this, in some sense, points back to where we started at the beginning of class, talking about treating a gravitational system as a point mass, which is very convenient and very much used in general relativity and in astrophysics in general. You can very well approximate a body in its gravitational pull with a point mass. But that proposal seems to fall apart when you actually start looking inside of bodies themselves, right? So when we're talking about the galaxy and almost treating it as a homogeneous object, right? And we're talking about what's going on within it, deep within it. Well, the problem is that we're treating that whole center as if it's a point at the center, right? We're treating all that mass as if it's a point at the center when we're calculating the necessity for this black hole to be whipping everything around it. And I wonder how valid that is if we start to think about these things as actually being more diffuse, and the bodies pulling on one another, and the bodies at the center being pulled by the bodies outside of them and exterior to them, and so forth. So time will tell how that plays out, but I think that's a central piece of this puzzle. All right. Now, in terms of the distribution of these, and maybe it would have made sense to mention this earlier, but when we're talking about the large-scale structure of this galaxy, we have this thin disk where the young stars are. And the young stars, the reason we think they're young is because they're rich in these heavy metals, which means that the metals had to have been made by an earlier star. So the young stars are thought to be young because they're obviously second, third generation stars, like the one that we have at the center of our solar system, right? It's got, well, just by evidence of our own planet, we've got a lot of stuff here that clearly wasn't made in our sun. It's not big enough to fuse the heavy elements, even the iron and the bigger metals that we see all over the place. So all those young stars are in the thin disk. It's very metal rich. And then the stars that are in the halo seem to have abundances of the heavier, of things. They have low abundances of these heavier elements, right? So we think they're old because it's sort of a catch-22, this argument too, and I apologize that it doesn't totally make sense, because I think it doesn't totally make sense. But we think that the older stars are essentially the ones that only have hydrogen and so forth, right? Because, well, they don't have the big heavy elements that they would need to have incorporated. But at the same time, if you were going to form a star brand new out of something, you would have to do it out of hydrogen if you were forming it away from all of this leftovers. And so this age argument for them is a little bit, there's some contradictions in there if you look really closely. So we tend to refer to the different aged groups by these names, population stars. So the bright blue stars in the spiral arms are called population 1s, and the stars in the halo and globular clusters are population 2. I don't know that you need to know that, but it's worth being acquainted for it. So the population 1 stars, heavy elements account for something like 1 to 4% of their total mass. Population 2 stars have less than like a 10 millionth of that, like something like 10 millionth as much iron as our sun, for example. So they're thought to be sort of cooling old stars. All right, I don't know if I want to get into the formation quite yet, because that might be a good place to talk about other galaxies as well. So needless to say, most of the formation models that were original, and I'll just preview this, we'll pick up with it next time. The basic formation model is very similar to the solar system formation model. You have this ball of, sort of unformed raw materials that collapses on itself and so forth. This is Kant's idea from the 1700s. What we're working towards in more modern times, now that we're able to see with good resolution a lot of other galaxies, is that galaxies actually seem to be interacting with each other. And we think that the actual interactions are giving them some of the shapes and some of the appearances that we're so fond of. And so we'll build that out next time, and we'll look at how these galaxies are possibly formed and how they relate to one another and how the bigger scale structures emerge, and particularly what we think is happening in the long run with this. We'll start talking about the actual redshift problem. And over the next couple of weeks, we're going to build towards this actual cosmology picture. So let's stop there for today, and I'll see you guys on Thursday. If anybody wants to come early, I will be here. I'm not going to make coffee, but we'll hang out.